Welcome to this video. In this video, we will be talking about interpolation using splines, so that by the end of this video, you will be able to interpolate data using both linear and quadratic splines. We now know ways to determine and evaluate an n-1 order polynomial for n given data points. We had the way of solving the linear system to find the coefficients of the normal form, and we already looked at the Lagrange form as well. But there was an issue that the larger the number of data points are, the larger the degree of the polynomial has to be, and the worse that interpolation polynomial becomes interpolating data between data points. So what do we do if we have very large data sets, like data sets of 1,000, 2,000 data points? Well, in that case, the idea is to split the data into subsets. Let's call those intervals. So if I have a data set starting with a data point x1, x2, x3, and I sort them in increasing values of x, interval 1 would be between the data points x1 and x2. And if I go to the ith interval, that would be between data points xi and xi plus 1, all the way to the n-first interval. That would be between x sub n-1 to all the way to x sub n. Okay, so if I have n data points, I will have n-1 intervals. Now, the idea is to do piecewise interpolation. And that's also known as spline interpolation, meaning we don't want to find an interpolation polynomial that interpolates over the entire data range, but we want to find an interpolation polynomial that interpolates the data in each interval separately only. Now, terminology, the data points where polynomials from adjacent intervals meet, we will call those data points knots. So basically, knots are the data points, all data points except for the two at the very first and the very end of the data set. Everything else is a data point where there is a left and a right interval that join together at the data point, and those data points are called knots. Okay, so let's start with the simplest first-degree polynomial. It's called linear splines. As the name implies, we're going to use first-order polynomials in each interval. Okay, so if I sketch this out here with the data sets, first-order polynomial is just a line. So within each interval, I'm going to approximate the data by a line. And that line, because it's interpolation, just connects the two data points that are at either end of the intervals. Now let me write this interpolation polynomial, and I'm going to just use Lagrange polynomials. So for the interval from xi to xi plus 1, right, that linear polynomial is supposed to go through the data points xi, yi, and xi plus 1, yi plus 1. And I'm going to call this the ith function f sub I. Using the Lagrange form gives me just f sub I of x is x minus xi plus 1 divided by xi minus xi plus 1 times yi, plus x minus xi times divided by xi plus 1 minus xi times yi plus 1. And this Lagrange polynomial is supposed to be valid in the interval where x is between xi and xi plus 1. Okay, what are the features of this linear spline? It's continuous, meaning adjacent polynomials will have the same value at the knots themselves. Right, so for the ith interval here, if I evaluate xi, yi, I should get the same value if I use the i-first interval and evaluate at xi, yi. These linear splines are easy to program. And linear splines give generally pretty good results if the data points are closely packed together. So if the process that you're describing with the data points is very well resolved by data points. Now, the downside of linear splines is, if you look at these linear splines drawn up there, there's a discontinuity of the slope at the knots, right? The slope of the lines just changes, jumps from one interval to the next. And in order to address this, we will have to go beyond first-degree polynomials to second-degree interpolation polynomials, or so-called quadratic splines. So the idea is just let's use a second-order polynomial in each interval. And we're going to use the standard form. So f of x is equal to some a times x squared plus bx plus ac. So let's look at the ith interval from xi to xi plus 1. I will have some function f sub I that is a quadratic function that has then a coefficient a sub I. The coefficient becomes a function of the interval that I'm in. So if I'm in the ith interval, I have a coefficient a sub I times x squared plus a b sub I times x plus a c sub I. And this polynomial will be valid in the ith interval from xi to xi plus 1. Now, we have n data points, meaning we have n minus 1 total intervals. And in each interval, we have A, B, and C. We have a total of 3 unknowns. N minus 1 intervals with 3 unknowns in each interval means that the total number of unknowns that we have is 3 times n minus 1, which is 3n minus 3 unknowns. Now, what are the conditions that let us determine these 3n minus 3 unknowns that define the quadratic spline in each interval? Well, first of all, the f of x must pass through the interval end data points. So meaning when I plug in xi, I want to get back yi. If I plug in xi plus 1, I want to get back the value of yi plus 1. So let's do this. Let's plug this in. So I get yi is equal to a sub I xi squared plus b sub I xi plus ci. And if I plug in xi plus 1, yi plus 1, I get yi plus 1 is equal to a sub I times xi plus 1 squared plus b sub I xi plus 1 plus ci. Okay, so the polynomial is supposed to go through the data values at the end of the interval. Now, those are 2 equations for each one of the intervals. So I have 2n minus 2 equations now. Not enough equations to determine the unknowns. So my second condition is that at interior knots, the slope, right, the slope is f prime, the first derivative of the quadratic function, which is 2ax plus b, of adjacent polynomials shall be equal. Meaning when 2 functions meet at a knot, they are supposed to have the same slope. So let's look at knot number I, which is the data point xi, yi. There's 2 functions that meet there, the quadratic function from interval I, f sub I, and the quadratic function from interval I minus 1, f sub I minus 1. And at that knot, at xi, yi, the slope of these 2 functions is supposed to be equal. So f prime of interval I minus 1 evaluated at xi is equal to the slope f prime of interval I, f prime I, evaluated at the same knot point xi. So let's plug this in. F prime at interval I minus 1 is 2 the coefficients from interval I minus 1, so 2a sub I minus 1 times xi plus b sub I minus 1, right? I'm in the I minus 1 interval. And that's supposed to be equal to f prime from the ith interval. So equal to 2 times a sub I times xi plus b sub I. So I have this type of equation for every knot. And the knots are just the interior data points, so total of n data points. 2 points at either end don't have a knot, are not a knot. So I have a total of n minus 2 equations that come from the requirement that the slope at knots is equal on both sides. So what's the number of equations that I have? Well, I have 2n minus 2 plus n minus 2 equation. So I have a total of 3n minus 4 equations for 3n minus 3 unknowns. So I need one more equation. Now, there's a choice here. one usually sets either the second derivative of the first interval to 0 or the second derivative of the last interval to 0. So what does that mean, that the second derivative is 0? That just means that the a is equal to 0, meaning we're going to use a linear function in the first or the last interval, thereby reducing the or adding one additional equation into the mix. So that would mean a1 is equal to 0 or a sub n minus 1 would be equal to 0. So now I have 3n minus 3 equations for my 3n minus 3 unknowns. So here are these equations just reorganized. For interval 1, I have that the first polynomial has to go through the two data values x1, y1, x2, y2. And I'm having the condition that a1, that coefficient there in the first interval, is equal to 0. And then I have 3 equations for each subsequent interval. And those are the equations that the function has to go through the endpoints and that the slope of the slope at knots for adjacent intervals has to be equal on either side. Now this defines a 3n minus 3 by 3n minus 3 linear system that we just have to solve for the unknowns ai, bi, and ci. And how do we solve linear systems? Well, with Gauss-Jordan using partial pivoting. Couple of coding comments when you try to code this up. The key to coding up spline interpolation is to set up the matrix A that you need to solve to find the coefficients. And at the same time, set up the right-hand side vector. And I'm going to call the right-hand side vector here G, because I've used the B for the coefficient that multiplies the x values in the quadratic spline. So let's start by defining an order of the coefficients in the vector of unknowns, and let's call the vector of unknowns Z. And really there you can choose whatever order you like. The most sensible way of ordering them might be in the way I've shown here. You write the coefficients for the first interval, a1, b1, c1, followed by the coefficients of the second interval, a2, b2, c2, all the way to the coefficients of the last interval, a sub n minus 1, b sub n minus 1, c sub n minus 1. Now, with that order defined, figure out the row number for each of the 3 equations for an arbitrary interval I. So let's start with interval 1. That will be the first 3 equations that in the matrix would be rows 1, 2, and 3. The second interval would have the next 3 equations, so that would be row numbers 4, 5, and 6. So if we go to interval I, that would then be the rows in the matrix, I minus 1 times 3, plus 1, plus 2, plus 3. Let's just try this out. If we plug in I equal to 2, we get 2 minus 1. That's 1 times 3 plus 1 is 4, 5, and 6. So that's what we had before. So that, for interval I, the row numbers in the matrix. And then what we have to do is figure out the column numbers for the ABC of interval I. And the column number in the matrix is basically just the entry number in the vector Z. So for interval 1, right, the entry numbers in the vector Z, for A1 is 1, for B1 is 2, and for C1 is the third entry in the vector Z. Interval 2, well, that would be 4, 5, and 6. So if we go to interval I, that means that the A sub I is an I minus 1 times 3 plus 1, the BI plus 2, the CI plus 3. And if you plug in interval 2, I equal to 2, you find that this gives you 4, 5, 6, like we identified before. Now, knowing the row and the column numbers sets the all entries of the matrix A. Right? And you can do this by initializing the matrix with all 0 values so that you then only need to set those values that are not 0. And then recall that interval 1 is a little bit different, right? Because we have this condition that A1 is equal to 0. We don't have that condition that the derivative at the knot is the same. But from interval 2 on, all the intervals are basically the same, and you can do this in a loop where the loop index I loops from 2 all the way to the last interval, n-1. Then, knowing the row numbers, what we do then is set the right-hand side values g, right, starting with a vector of all zeros pre-allocated again. And then all we have to do is solve this system using a call to my Gauss-Jordan. Thank you for watching.